Okay, this is October 2nd, 2014. We're talking about the practice sheet on average atomic mass. A quick reminder about what percents really mean and how to convert those to decimals. Now, setting up the first one. So that's your setup. And inherent in this is that that's 89.5 divided by 100 times 60. So you're already dividing these things out. You don't have to divide these by 3. There's no division necessary. All you're doing is multiplying by the abundance expressed as a decimal and adding them up. Okay, so when we do the math, we get 59.8125 units, of course, are AMUs. That's our average atomic mass. The question was asked, should we sig fig these? I wrote the first 2 questions, and I gave you enough decimals that you can do sig figs and get a reasonable mass. The last 2 questions I borrowed from another chemistry teacher, and he didn't put enough sig figs in on the masses. Those masses would probably have more sig figs. So, this is what you get ignoring the atomic mass. You were given 60.0. You can have 3 sig figs. Oh, well, assuming that I had not screwed that up and given you an extra sig fig there, which I intended to. Having 3 sig figs, you get 59.8 AMUs. So that's pretty reasonable sig figs on this. You shouldn't ignore sig figs. The answers I put up in my key show a raw answer, and it says ignoring sig figs, because especially on those last ones, like you've got 1 sig fig with titanium 50. That's ridiculous. That doesn't give you anything useful. So, questions on how to do these? I can. Here's what I want. I should have reordered those because 14 turns everything on its head. So, were you able to do 15 and 16? Okay. Skip 14, do 15 and 16 to make sure you can do this in forward, and then we'll reverse it and do 14 together, okay? For number 14, we've turned this on its head a little bit. And you have this generalized formula that the percentage abundance expressed as a decimal times the mass of that particular isotope plus, lather, rinse, repeat, percentage times mass equals your average atomic mass. So you have this general sort of formula, and you can do this with as many isotopes or as few isotopes as exist. Whether it's 2 isotopes or 10 isotopes, you can do this. Well, now what you're given is the abundance and the mass of 2 isotopes, the mass of a mystery isotope, and the average. So you just have to solve for that x. So the way that we would set this up is as follows. 0.672 times 130 plus 0.105 times 67.2 plus x, because we don't know what the percentage abundance is. Plus x. Wait, did I screw something up?
Yeah, the 67.2.
Oh, geez. Where did I get that from? That should be 131. I'm transposing numbers. I do apologize. Whew. Thank you. Okay. There we go. Oh, better? Okay.
67.2 corresponds to 130.
Yes?
10.5 corresponds to 131.
Right? That's what I have now. Okay, we're good? Okay.
I thought it was okay before.
No, it was not at all. Okay. X times 133. And we have our average. I'm going to shrink this so I can fit it in. Oops. And our average atomic mass is 132.04 AMUs. Okay. So it's just algebra at this point. X is equal to, and I'm gonna do the the shortcut and then I'll walk back through. No, don't do that, Moser. Don't do that, Moser. Okay, so if we start to move toward isolating x, subtract this and that from each side. So we get x times 133 is equal to 132.04 minus 0.672 times 130 minus 0.105 times 131. Okay? Well, now if we divide both sides by 133, we've isolated x. And so what you get there is the percentage abundance expressed as a decimal. So you get something like, what is it, 0.235? 2325, okay. Et cetera, et cetera, et cetera, is equal to x. So multiply that by 100 and you get a percentage of 23.3. Right, but you've got a lot fewer numbers to work with in your raw answer. So, because recognize that all the rest of those are rounded. That seemed fairly straightforward. Okay. So we're going to go over the FIP quiz here. We'll see if I can... Okay, that's the quiz. Yeah, now we're going to start to talk about the moles! Yay! We can't even see them, but we can count them. What? Does that strike anybody else as conceptually strange? That this thing that you can't photograph, you can't I mean, you have to visualize, you can't see it, and yet we can give an exact number of them? It's kind of crazy, but we can. As long as we know the sample and the composition of a piece of matter, we can tell you exactly how many atoms are there. That's crazy. Now, how do we do that? The mole! This is a star-nosed mole. It's a native Ohio mammal, little rodent. This is the International Star-Nosed Mole greeting. But aside from the cute, furry, musky little creature, it's an SI unit. And this is the unit amount of a substance. To think about a mole, think about a dozen. How many apples are in a dozen apples? 12. How many ears of corn are in a dozen ears of corn? How many donuts are in a dozen donuts? 12. How many dirty socks are in a dozen dirty socks? 12. You know, how many rabid chipmunks are in a dozen rabid chipmunks? 12. A mole's the same way. It's just a way to describe a set number of things. And this definition always confounds people. It seems like you're making a circular definition. If we take carbon-12, if we can get a chunk of 12.0 grams, that's all carbon-12. No carbon-13, no carbon-14, just carbon-12. And we can count the number of pieces there. That is 1 mole of pieces. And this is the number of things in a mole. 6.022 times 10 to the 23rd pieces. Okay? So a dozen is 12. A mole is 6.022 times 10 to the 23rd. A ream is 500. Did you all know that? For paper. Like a ream of paper is 500 sheets. A dozen donuts is 12 donuts. And a mole of anything is 6.022 times 10 to the 23rd. Anything, 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 any single thing that you can come up with, a mole of it is 6.022 times 10 to the 23rd. That seems really obvious, but it's not. Somehow it gets lost in the shuffle. So that's just the thing to remember. It's like a dozen. It's just the number of pieces. It's just a description of a number of pieces. So we have rabid chipmunks, we have, bowling balls, we have whatever. A mole of them is 6.022 times 10 to the 23rd of that. Avogadro's number, and this is named for, let's see if I can get all his names. Emilio something Avogadro. Okay. I didn't get all his names. He's got like 6 names. Italian nobility from like the 14th century, 15th, no, 17th century? Anyway, he's an old Italian dead guy. Nobility, he's got a bunch of names because, of course, you know, some sort of aristocratic family, and they've got to slap every name on you they can. He was the first one to conceptualize this. He did not invent this, okay? He did not invent it. He didn't even know about atoms. He didn't come up with this number. Don't you ever tell me that Avogadro invented this number. No. Avogadro counted the number of things in a mole. No. But his work laid the sort of philosophical groundwork for this number. So we call it Avogadro's number, and it's just the name we give to the number of pieces in a mole. So a mole is not 6.022 times 10 to the 23rd. A mole is 6.022 times 10 to the 23rd of something. The number itself is Avogadro's number. It seems like a subtle distinction, but there it is. Okay, so the molar mass is the mass of 1 mole of something. So we could take the molar mass of a mole of rabid chipmunks. We could take the molar mass of a mole of dirty socks. However, all socks are different, all chipmunks are different. Depends on how much grain they've had. If you look at the periodic table, and for right now you can use the one in your agenda. Let's take as an example, let's go ahead and use lithium. So we've got lithium with an atomic number of 3 that tells us how many protons it's got, and this average atomic mass of 6.94. That's the atomic mass is 6.94 AMUs, right? Because we measure atomic mass in atomic mass units. So creative. If we had 1 mole of lithium, it would have a mass of 6.94 grams. So the molar mass is the same as the atomic mass, but it's got different units. Now, what that, let me see if I can copy this. Take it to the next slide. Okay, there we go. When we talk about the molar mass of something, the units we typically use are grams per mole. Because what we're saying about lithium is that there are 6.94 grams of lithium in every 1 mole of lithium. Okay? So the units for molar mass are grams per mole. We can say 1 mole of lithium has a mass of 6.94 grams. But when we talk about molar mass, we want to pay attention to those units. Those units will save your life later, so you really do want to kind of focus on what they are. And I will slip up too and just write grams. Feel free to correct me. Somewhere in your life there's a GMA or a GMA-like figure. Yeah, grandma. Some people actually call them GMA. I say GMA because this is a handy way to keep your brain in order when doing conversions. So, this is grams, moles, atoms. You will probably want to write that on the top of your quizzes and your tests. This is a way to remember the steps you have to take when doing conversions. So I said we can count how many atoms are in a sample of anything if we know its mass and we know what it is. It's all because of that relationship of molar mass and Avogadro's number and atomic mass. So let's start practicing. So if we want to figure out how many moles of something we have, we can go from grams straight to moles because there's a relationship between grams and moles. Okay? We know that there's a relationship. That relationship is molar mass. So if you have 22.5 grams of calcium, and you want to know how many moles that is, molar mass becomes your conversion factor. This is a factor label setup, so we know that the units and the chemical that go down here have to be the same so that they cancel out. So we'll have grams of calcium down there. And the relationship, the conversion factor we're using is moles and grams. And if we stop right there, we end up in moles of calcium. That's the unit we want to be in. Unit and chemical. So, where do we get the numbers to plug in here? The periodic table. Or they're given to you. And very often at this stage of the game, I give you the molar mass because you haven't gotten your first periodic table from me yet. You've got the one in here. I've got some quibbles with the way they do molar mass, but you know, whatever. What do I know? So, molar mass of calcium, 40.08 grams in every 1 mole. 40.08 grams in every 1 mole. So we get 0.561 moles of calcium. I don't know if that's with proper, if that's the raw answer. I mean, that's proper sig figs. No, okay, so it was 0.561377246. So that's sig figged. A word about sig figs. When you're using a conversion factor, like something you got off the periodic table, that's assumed to have infinite sig figs. Those conversion factors are assumed to kind of be perfect. So your sig figs are going to come from your given. Okay? Conversion factors don't count against you for sig figs. I mean, because if they did, hey, there's 1. Well, we can't do that. That's just silly. Okay. So we use our molar mass here. We get a raw answer. And our final answer with sig figs would be 4.58 moles of carbon. Okay. That's our first kind of conversion. There is, but remember, looking at this GMA, you can go straight from grams to moles. Straight from grams to moles. There's no middle step. That also means you can go straight from moles to grams. So let's look at one of those. Okay, so here's your example. It's another factor label. Find the mass in grams of 2.5 moles of calcium. 2.5 moles of calcium is our given. The relationship that we're using, the conversion factor, is molar mass. And then we get an answer. We have to sig fig it. That's an ugly one for sig figs, but we'll take care of that. So we always start with our given. 2.5 moles calcium, units and chemical. Units and chemical down here to cancel are going to be moles of calcium. And we want to end up in grams of calcium. Notice that we just used this in the inverse. We just used it where the mass was on the bottom and the moles were on the top. It depends on what direction you're going. That's where if you pay attention to your units and make sure they cancel, the problems solve themselves. Okay, we have to go, I have 1 mole of calcium. There's never going to be a different number there. And the molar mass of calcium is 40.08 grams per mole. So what's our raw number? 2.5 divided, or whoops, 2.5 times 40.08. Oh, that's our raw answer. Okay. How many sig figs can we have? 2. So this would have to be 1.0 times 10 to the second grams of calcium. It's the only way to do that one with correct sig figs. Do you want to practice one more? So this is for GMA. This is moles to grams. Yes, sir. And just to refresh on factor labels, once you've made sure that your units cancel and you're in the units and chemical you want, you're just multiplying everything across the top, multiplying everything across the bottom, and dividing top by bottom. So obviously on the bottom we've just got a 1, so it's just multiplication. Okay, let's practice one more mole to gram. Okay, you just brought in 15.72 moles of aluminum to the recycling center. What's the mass of aluminum that you just brought in. We always start with our given. So first box is going to be 15.72 moles of aluminum. We know that we're going into grams of aluminum. The conversion factor that we want is molar mass. What units in chemical are going to go down on the bottom to cancel? Moles of aluminum. What units in chemical are going to go on the top? Grams of aluminum. Okay, where does that relationship come from? Periodic table. So for aluminum, 26.98 grams in 1 mole. Do our units all cancel? Units in chemical? Yes. Do we end up in what we want to end up in? Yes. Let's get a raw answer. Okay, I get a raw answer of 424.1256 grams of aluminum. How many sig figs can we have? 4. So our final answer would be 424.1 grams of aluminum. Okay. All right, so we'll pick it up tomorrow with some additional work. I've got a practice sheet here for you. I will hand it to you now. Go through and pick out the ones that are just gram to mole and mole to gram so that you can carve those in right now. And then when we start the next sets of conversions tomorrow, you can do the rest of them.